The truth about stealth aircraft, F-35, B-2, and Radar Explained. Full 2-hour guide. What if the most advanced aircraft ever built were never truly invisible? For decades, the idea of stealth has captured imagination like almost no other technology in modern warfare. The belief that somewhere above the clouds, there are machines that cannot be seen, cannot be tracked, and cannot be stopped. But here is the reality that almost nobody explains clearly. Stealth is not invisibility. It never was, and it was never meant to be. And yet, despite that misunderstanding, billions and even trillions of dollars have been invested into making aircraft harder to detect. Not impossible to detect, but harder. Just enough to gain an advantage in the most critical moment of any engagement, the first detection. Because in modern air combat, the first sight that sees the other wins. Not always, but often enough that entire strategies, entire aircraft designs, and entire defense systems are built around that single moment. So today, we are going to break this down completely. No hype, no myths, no cinematic exaggeration, just engineering, physics, and real system-level thinking. You're about to see how stealth actually works, why aircraft like the F-35, F-22, and B-2 are designed the way they are, how radar systems try to find them, how AWACS changes the entire battlefield, and why even older non-stealth aircraft like the F-15 and F-18 are still extremely relevant in modern warfare. And by the end of this video, you will understand something that most people never fully grasp. Stealth is not about disappearing. It is about controlling information. Before we go deeper, if you want real engineering breakdowns like this, without clickbait, without oversimplification, and without the usual myths, make sure to subscribe because this channel is focused on explaining how complex systems actually work, not just what they look like. Now, let's start with the foundation. What is stealth really? At its core, stealth is about reducing something called radar cross-section, or RCS. This is not the size of the aircraft physically, but how big it appears to radar systems. Imagine shining a flashlight at a mirror versus shining it at a rough surface. The mirror reflects light directly back at you. The rough surface scatters it in all directions. Radar works in a similar way. Traditional aircraft with vertical surfaces, exposed weapons, and complex geometry tend to reflect radar waves back toward the source, making them easy to detect. Stealth aircraft are designed to avoid that. They use angled surfaces, smooth shapes, and internal weapon bays to redirect radar energy away from the emitter instead of back toward it. But here's the key point that is often misunderstood. The energy does not disappear, it just goes somewhere else. So stealth is not invisibility, it is redirection. And now combine that with materials, radar-absorbent coatings that convert some of that energy into heat, and you get an aircraft that is significantly harder to detect, but still not impossible to detect. And this is where things start to get interesting. Because radar itself is not a single system, it's a spectrum of technologies, different frequencies, different wavelengths, different power levels, and different strategies. High-frequency radars are very precise, but struggle with stealth shaping. Lower-frequency radars can detect stealth aircraft better, but with less accuracy. So already we see a trade-off. Stealth aircraft are optimized against certain types of radar, but not all of them at the same time. And that leads to a constant technological competition. Stealth improves, radar adapts. Stealth evolves again, radar evolves again. This is not a solved problem, it is an ongoing race. Now let's talk about one of the most important ideas in modern aviation, sensor fusion. Because stealth alone is no longer enough. Aircraft like the F-35 are not just designed to avoid detection, they are designed to understand the battlefield in a way that older systems simply cannot. Instead of relying on a single radar or a single sensor, modern systems combine multiple inputs: radar, infrared, electronic signals, and even data from other platforms into one unified picture. This means that even if one system fails or is limited, another can compensate. And more importantly, it means that pilots are no longer just flying aircraft, they are managing information. This is where the concept of the aircraft as a node in a network becomes critical. The F-35, for example, is often described as a flying sensor platform as much as a fighter jet. It collects data, processes it, and shares it with other assets, including other aircraft, ground systems, and airborne platforms like AWACS. And this changes everything, because now detection is no longer just about one radar finding one target. It is about a network of systems working together to build a complete picture. And this brings us to AWACS. Airborne warning and control systems are essentially flying radar platforms designed to monitor vast areas of airspace from high altitude. They can detect targets at long ranges, track multiple objects simultaneously, and coordinate responses across entire formations. But even AWACS has limitations. It is powerful, but it is also a large, highly visible asset, and while its radar can detect stealth aircraft under certain conditions, it does not guarantee early detection, especially against well-designed stealth platforms. So again, we see balance. Every advantage introduces a new vulnerability. Now let's go deeper into stealth aircraft themselves. Take the F-35, for example, one of the most advanced and controversial aircraft ever built. Its design prioritizes a combination of stealth, sensor fusion, and multi-role capability. It is not the fastest aircraft, it is not the most maneuverable in traditional terms, but it is designed to operate in a highly connected environment where information is more valuable than raw performance. Its shape reduces radar returns from specific angles, its materials absorb part of incoming energy, and its systems are optimized to minimize emissions when needed. But it still produces heat, it still interacts with the environment, and under the right conditions, it can be detected. The same applies to aircraft like the B-2 Spirit, which uses a flying wing design to minimize radar reflection, and the upcoming B-21 Raider, which pushes those concepts even further. These aircraft are incredibly difficult to detect, especially at long range, but not impossible. And that brings us to one of the most important realities in modern air combat. Detection is not binary. It is not visible or invisible, it's a spectrum. At long range, a stealth aircraft might be effectively invisible to certain radars. At medium range, it might appear as a weak, inconsistent signal, and at close range, it can be tracked more reliably. So the goal of stealth is not to eliminate detection entirely, but to delay it long enough to gain a tactical advantage. Now, let's compare this to non-stealth aircraft, like the F-15 and F-18. These aircraft do not attempt to hide in the same way. Instead, they rely on speed, maneuverability, electronic warfare, and tactics. They can be detected more easily, but they also have systems designed to respond to that detection: warning receivers, countermeasures, and coordination with other assets. In many scenarios, these aircraft are still extremely effective, especially when supported by a network of sensors and electronic warfare systems. So the idea that non-stealth aircraft are obsolete is simply not accurate. They are different tools for different missions. And in a complex environment, diversity often matters more than specialization. Now, let's address the bigger question. Why invest so much into stealth if it is not perfect? The answer is timing. If you can delay detection by even a few seconds or minutes, you can position yourself better, launch first, or avoid engagement entirely. In high-speed environments, those moments matter. They can define the outcome of an entire mission. And this is where the concept of information advantage becomes critical. Stealth aircraft aim to see without being seen for as long as possible. Radar systems aim to detect as early as possible. AWACS aims to coordinate everything, and electronic warfare aims to disrupt all of it. This is not a simple battle between two technologies, it is an ecosystem of interacting systems. and understanding that ecosystem is the key to understanding modern air combat. Now, as we move into the next sections of this video, we're going to go much deeper. We will break down specific aircraft design choices. We will look at how radar systems actually process signals. We will explore thermal detection and infrared tracking, and we will analyze how all of these elements come together in real scenarios. But before we continue, here's something to keep in mind. Everything you're about to see is part of a much larger system. No aircraft operates alone. No radar works in isolation, and no single technology determines the outcome. It is always about integration, coordination, and timing. So, if you're ready to go beyond the myths and actually understand how stealth, radar, and modern air combat work in practice, let's move into the first chapter, because this is where things stop being theoretical and start becoming real. The F-35 Stealth Explained, how it's actually detected. What if I told you the most advanced stealth fighter in the world isn't actually invisible? For decades, stealth technology has been marketed as something close to magic, aircraft that simply vanish from radar screens. But the reality is far more complex, and honestly, far more interesting. Because the F-35 Lightning II isn't invisible. It's engineered to be hard to detect, not impossible to find. And today, we're breaking down exactly how it works, and more importantly, how modern systems can still detect it. But before we go deeper, if you're into real engineering, real physics, and the truth behind military technology, make sure to subscribe. Most people watching aren't subscribed, and you don't want to miss what's coming next. Let's begin. To understand how the F-35 can be detected, you first need to understand what stealth actually means. Stealth is not invisibility, it's reduction. Specifically, reduction of something called radar cross-section, or RCS. This is essentially how visible an object is to radar. A normal aircraft reflects radar waves back to the source, making it easy to track. The F-35 is designed to do the opposite. Its shape, its materials, and even its panel edges are all carefully engineered to scatter radar waves away from the source. Instead of bouncing signals back, it deflects them in different directions. That's why, from certain angles, it can appear incredibly small on radar, sometimes comparable to a bird. But here's the key point. That only works under specific conditions. Because radar is not just one system. There are many types of radar, and some of them are much better at detecting stealth aircraft than others. Let's talk about the first major weakness, low-frequency radar. Most stealth aircraft, including the F-35, are optimized to evade high-frequency radar, the kind used in fire control systems. But low-frequency radar operates differently. It uses longer wavelengths, and those wavelengths interact with the aircraft in a way that makes stealth shaping less effective. Instead of being scattered cleanly, the waves can resonate with the structure of the aircraft, which means detection becomes possible. Now, this doesn't mean low-frequency radar can lock on and guide a missile easily, but it can detect something is there, and that's all you need to start tracking. Now let's move to another factor, infrared detection. Even if radar struggles, physics still applies. The F-35 generates heat, from its engine, from air friction, and from internal systems. This heat creates an infrared signature. Modern infrared search and track systems, known as IRST, are designed specifically to detect this. And unlike radar, they don't emit anything, which means they're passive, silent, undetectable. So even if an aircraft avoids radar, it can still be seen through its heat signature, especially at long distances and high altitudes. But it gets even more interesting because detection isn't just about one system anymore. Modern defense networks combine multiple sensors, radar, infrared, electronic intelligence, even data from satellites. This is called sensor fusion. Instead of relying on one method, they combine everything. So even if the F-35 reduces its radar signature, another system might still pick up something. And when all that data is combined, a picture starts to form. Not perfect, but enough. Now let's talk about something most people don't consider: angle. Stealth is highly dependent on geometry. The F-35 is optimized for frontal stealth, meaning it's hardest to detect from the front. But from the sides or rear, its radar signature increases. This is especially true when the aircraft is maneuvering, because as it turns, different surfaces reflect radar differently, which creates moments of increased visibility. Short windows, but enough for advanced systems to exploit. There's also the issue of external factors: weather, atmospheric conditions, electronic interference. All of these can affect how radar waves behave, sometimes helping detection, sometimes reducing it. But the key takeaway is this: stealth is not a constant. It changes depending on the environment. And then there's one of the biggest misconceptions of all. People think stealth makes an aircraft untouchable. But in reality, stealth is just one layer of survivability. The F-35 also relies on electronic warfare systems, advanced sensors, situational awareness, and networked data. It's not about being invisible. It's about being harder to target and faster to react. So can the F-35 be detected? Yes. Under the right conditions, with the right systems, it absolutely can. But detection doesn't equal destruction. Finding something is one thing. Tracking it precisely and engaging it effectively is something else entirely. And that's where the F-35 still has a massive advantage. But here's the bigger picture. Modern warfare is evolving. It's no longer about single systems. It's about networks, data, integration, and adaptation. Stealth is still powerful, but it's no longer unbeatable. And this is just the beginning, because new technologies are already changing the game. Quantum radar, AI-assisted tracking, next-generation sensors. The future of detection is evolving just as fast as stealth itself. If you've made it this far, you're already ahead of most people watching. So here's the question: is stealth still worth it, or is it becoming obsolete? Let me know what you think. And if you want to see how infrared systems specifically track stealth aircraft, or how modern radar networks actually work in real scenarios, make sure you subscribe, because the next video is going even deeper. And trust me, you don't want to miss it.
The F-35 Lightning II, a masterclass in aerospace engineering. Aviation has always been defined by the relentless pursuit of the next frontier. From the fabric and wood of the early 20th century to the supersonic aluminum structures of the Cold War, aerospace engineering has consistently pushed the boundaries of what is physically possible. Today, we stand at the pinnacle of this century-long evolution. Before us is the F-35 Lightning II. To call it an aircraft is mathematically accurate, yet fundamentally incomplete. It is, more accurately, a highly advanced integrated flying data center. It represents a paradigm shift in aviation design, moving away from pure kinematic performance, how fast an aircraft can fly or how tightly it can turn, and toward information dominance, sensor integration, and low observable technology. In this comprehensive engineering analysis, we will deconstruct the F-35. We will look past the composite skin and delve into the complex mechanics, thermodynamics, and software architectures that make this machine operate. We will explore how thousands of individual components, from the articulating titanium fan blades to the microscopic layers of radar-absorbent materials, operate in perfect synchronization. This is not a story of hardware alone. It is a story of unprecedented computational power, advanced fluid dynamics, and a unified design philosophy that has resulted in the most complex aerospace platform ever realized. Welcome to the architecture of modern flight. Development history. The genesis of the F-35 lies in a procurement initiative known as the Joint Strike Fighter, or JSF program, initiated in the 1990s. The engineering challenge presented to the aerospace industry was unprecedented in its scope. The objective was not simply to build a new aircraft, but to engineer a single baseline platform that could satisfy the distinct operational requirements of three different operational branches. Historically, aircraft were highly specialized. An airframe designed for conventional runways was fundamentally different from one designed to endure the extreme mechanical stresses of aircraft carrier launches, which in turn was entirely different from an aircraft capable of hovering like a helicopter. The JSF program demanded all three capabilities from a single core design. This requirement led to the development of three distinct variants: the F-35A, designed for conventional takeoff and landing, the F-35B, engineered for short takeoff and vertical landing, and the F-35C, optimized for carrier-based operations with larger wing surfaces and reinforced landing gear. To achieve this, engineers utilized advanced computer-aided design to create a modular airframe. This meant the central fuselage, the cockpit, and the primary avionics systems remained largely identical across all variants, while the propulsion integration and lifting surfaces were adapted. During the competitive phase, two distinct design philosophies emerged: the X-32 and the X-35. The X-35 ultimately demonstrated a more stable approach to the vertical landing requirement through an innovative shaft-driven lift fan concept, a mechanical marvel we will explore in detail later. The transition from the X-35 prototype to the final production F-35 required years of rigorous refinement, transforming a proof of concept into a reliable, integrated, and highly sophisticated aerospace vehicle. Aerodynamic design. The physical shape of the F-35 is a masterclass in aerodynamic compromise. In aerospace engineering, every curve and angle is a negotiation between lift, drag, and stealth. Unlike older generations of aircraft, which often featured external payload stations and auxiliary fuel tanks, the F-35 relies heavily on a blended wing body design. The fuselage transitions seamlessly into the wings, creating a continuous aerodynamic surface. This not only increases internal volume for fuel and operational equipment, but also significantly reduces aerodynamic drag. Notice the nose of the aircraft. It features a distinct horizontal ridge known as a chine. In flight, particularly at high angles of attack, these chines generate powerful vortexes, spiraling tubes of low-pressure air. These vortexes travel aft over the wings, re-energizing the boundary layer and providing the aircraft with remarkable stability and lift at low speeds, preventing aerodynamic stalls. The internal storage bays are a critical aerodynamic feature. By carrying equipment internally rather than on the wings, the F-35 maintains an exceptionally clean aerodynamic profile. This pristine shape ensures that the airflow remains largely laminar or smooth over the skin of the aircraft. The control surfaces, the ailerons, horizontal stabilizers, and the twin outward-canted vertical tails are entirely governed by a complex fly-by-wire system. The pilot does not mechanically move these surfaces. Instead, the pilot inputs a desired trajectory, and the flight control computers calculate exactly how many degrees each surface must deflect to achieve that maneuver, compensating for airspeed, altitude, and air density in milliseconds. The canted tails specifically provide immense directional stability while contributing to the aircraft's overall low observable shaping.
Stealth technology. Perhaps the most discussed yet least understood aspect of the F-35 is its low observable or stealth technology. Stealth is not invisibility. It is the science of delaying detection by manipulating the electromagnetic spectrum. Radar systems operate by emitting electromagnetic waves and measuring the reflections that bounce back from an object. The larger the reflection, the larger the radar cross-section, or RCS. The engineering goal of the F-35 is to minimize this RCS to the size of a very small bird or an insect. This is achieved through two primary engineering principles: shape and materials. First, consider the shape. The entire airframe is designed using a principle called continuous curvature and edge alignment. If you draw a line along the leading edge of the right wing, you will find it is perfectly parallel to the trailing edge of the left wing. The access panels, the landing gear doors, and even the internal equipment bay doors feature serrated, zigzag edges. These angles are precisely calculated to reflect incoming radar waves away from the receiver, rather than bouncing them directly back. Second, we examine the materials. The skin of the F-35 is manufactured from advanced composite structures and coated with radar-absorbent material, or RAM. While the exact chemical composition remains highly classified, the physics behind it is clear. RAM contains microscopic particles, often carbon or iron-based, suspended in a dielectric matrix. When a radar wave penetrates this coating, the electromagnetic energy oscillates the particles. This friction converts the electromagnetic energy into a minute amount of thermal energy, effectively absorbing the radar wave. However, stealth also requires thermal management. Jet engines produce immense heat. To reduce its infrared signature, the F-35 employs a highly advanced thermal management system. Fuel acts as a primary heat sink. Before it is burned in the engine, the cold aviation fuel is cycled through heat exchangers to cool the aircraft's powerful avionics and sensors, while the engine exhaust nozzle is designed to mix bypass air with the hot exhaust, rapidly dissipating the thermal plume into the atmosphere.
Engine and power system. The heartbeat of the F-35 is the Pratt & Whitney F-135 turbofan engine. It is recognized as one of the most powerful fighter engines ever produced, capable of generating over 40,000 pounds of thrust. The F-135 is a low-bypass turbofan. air enters through the two bifurcated intakes, which use a diverterless supersonic inlet design to strip away turbulent boundary layer air, and is compressed through multiple stages of titanium fan blades. In the combustion chamber, this highly compressed air is mixed with fuel and ignited. The expanding gases rush backward, turning the turbine section, which in turn powers the front compressor, before being expelled through the rear nozzle. The materials inside the high-pressure turbine operate in an environment where temperatures far exceed the melting point of the metals themselves. Engineers solved this thermodynamic paradox by growing single-crystal turbine blades and using complex internal cooling channels, allowing microscopic films of cooler air to protect the metal from the superheated gas. The most spectacular mechanical achievement in the F-35 family belongs to the STOVL variant, the F-35B. To achieve vertical flight, the engine utilizes a patented three-bearing swivel module. The rear exhaust nozzle can articulate downwards in just 90 degrees in seconds. Simultaneously, a complex mechanical clutch engages, connecting a drive shaft from the main engine to a massive lift fan located directly behind the cockpit. This lift fan, featuring counter-rotating blades, pulls cold air from above the aircraft and forces it downward, providing a massive pillar of thrust. Together with small roll post thrusters under the wings for lateral stability, the F-35B achieves a perfect balance, allowing a multi-ton machine to hover motionless in the sky.
Sensor systems. If the engine is the heart of the F-35, its sensor suite is its nervous system. This aircraft is designed to gather, process, and distribute an unprecedented volume of data regarding its surrounding environment. The primary active sensor is the AN/APG-81 Active Electronically Scanned Array, or AESA, radar. Older radar systems used a single large dish that mechanically tilted and panned. An AESA radar, by contrast, contains over 1,000 individual solid-state transmit and receive modules. By subtly shifting the timing of the electronic signals sent to these modules, the radar beam can be steered instantaneously in any direction without any moving parts. This allows the F-35 to scan the airspace, map the ground, and track multiple targets simultaneously with incredible precision and minimal energy emission. Beneath the nose is the Electro-Optical Targeting System, or EOTS. Housed behind geometric, faceted sapphire glass, this system provides high-resolution, long-range infrared and optical imaging. But the true innovation is the Distributed Aperture System, or DAS. 6 high-resolution infrared cameras are seamlessly integrated into the skin of the aircraft, providing a continuous 360-degree spherical view of the environment. The DAS operates autonomously, constantly monitoring for thermal anomalies, tracking other aircraft, and providing navigational visual data. The brilliance of the F-35 lies in sensor fusion. In older aircraft, a pilot had to look at a radar screen, a separate infrared screen, and a separate data link screen, mentally combining the information. The F-35's central computers do this heavy lifting. They ingest the data from the AESA radar, the EOTS, the DAS, and external data feeds and fuse them into a single, cohesive, highly intuitive graphical interface.
Cockpit and pilot interface. The interface between the human operator and this immensely complex machine is a marvel of ergonomic and software design. Upon entering the F-35 cockpit, the first thing one notices is the absence of traditional dials, gauges, or physical switches. The entire instrument panel has been replaced by the panoramic cockpit display. This is a single large piece of continuous glass featuring full touchscreen capabilities.
The pilot can customize this digital workspace, organizing the layout of navigation maps, sensor feeds, and system diagnostics with the swipe of a gloved finger, much like operating a tablet computer. However, the most critical piece of interface technology is worn by the pilot. The F-35 does not feature a traditional head-up display mounted on the dashboard. Instead, all critical flight data, airspeed, heading, altitude, and targeting information is projected directly onto the visor of the Generation 3 helmet-mounted display system. Because this helmet is integrated with the aircraft's DAS cameras, an extraordinary capability is unlocked. If the pilot looks down at their feet, the helmet displays the camera feed from the belly of the aircraft. The pilot can essentially see right through the solid structure of the airframe, gaining unimpeded situational awareness in every direction. The helmet is custom-fitted to the precise biometric measurements of each individual pilot's head to ensure the optical projections align perfectly with their pupils.
Software and data systems. The F-35 is fundamentally a software-defined aircraft. The physical hardware is largely a conduit for the millions of lines of sophisticated code that govern every aspect of its operation. To put this in perspective, the flight control and mission systems rely on over 8 million lines of software code, significantly more than any previous aerospace platform. This immense computational capability allows the aircraft to operate as an advanced network node. Through secure, high-bandwidth data links, an F-35 can silently share its fused sensor picture with other aircraft, naval vessels, and ground-based control centers. It acts as an airborne quarterback, analyzing the environment and distributing critical information to allied platforms, enhancing the situational awareness of the entire network. Furthermore, software governs the aircraft's maintenance and life cycle through systems like ALIS, the Autonomic Logistics Information System, which is currently transitioning to the cloud-based Odin network. The aircraft constantly monitors the health of its own components. If a specific valve or sensor is showing signs of degradation, the aircraft software will log the anomaly, automatically transmit a diagnostic report to the ground crew, and even check the global supply chain for a replacement part before the aircraft has even landed. This predictive maintenance is a revolution in operational efficiency.
Comparison with other aircraft. To fully appreciate the engineering of the F-35, it is instructive to compare its design philosophy with other contemporary aerospace platforms. Consider the F-22 Raptor. Designed primarily for extreme high-altitude performance and high-speed maneuverability, the F-22 relies on raw kinetic energy and thrust vectoring muzzles for physical dominance. The F-35, by contrast, is optimized for multi-role versatility and information superiority. While highly maneuverable, the F-35's priority is not pure speed, but rather maintaining a low radar signature while processing vast amounts of environmental data. When comparing the F-35 to advanced delta-wing platforms like the Eurofighter Typhoon, the engineering divergences are clear. The Typhoon utilizes a canard delta configuration to achieve incredible aerodynamic agility and climb rates. However, it features external payload stations and a higher radar cross-section. The F-35 sacrifices some of that absolute aerodynamic agility in favor of strict internal carriage and stealth shaping, relying on its sensors to identify variables before it is ever detected. Similarly, compared to platforms like the S-570, which features heavy emphasis on thrust vectoring and mechanical maneuverability, the F-35 relies entirely on its sensor fusion and secure networking capabilities. The engineering consensus of the F-35 program is that modern aerospace operations are decided by computing power and data integration, rendering mechanical dogfighting metrics secondary to electronic and informational supremacy.
The F-35 Lightning II is far more than a collection of advanced materials and powerful engines. It represents a fundamental evolution in how we conceive of aerospace engineering. It is the realization of decades of research into fluid dynamics, electromagnetics, thermodynamics, and computer science, fused into a single, cohesive platform. By prioritizing stealth, sensor integration, and software architecture over traditional kinetic metrics, engineers have created a system that perceives the environment with unparalleled clarity. The challenges involved in its development were staggering, requiring the aerospace industry to invent new manufacturing techniques, write millions of lines of code, and push the boundaries of material science. The result is an aircraft that operates not just within the physical atmosphere, but within the complex digital networks of modern operational environments. As we look toward the future of aviation, the architecture of the F-35 will serve as the foundation for the next generation of flight. It stands as a profound testament to human ingenuity, a seamless integration of human intelligence and machine capability, flying silently at the edge of the stratosphere.
Of advanced aeronautics, invisibility is a common term, but a technical misnomer. No object is truly invisible to all forms of detection. Instead, modern aircraft like the F-35 are designed to manage their signatures, the various signals they emit or reflect into the environment. For decades, the primary focus of engineering was the radio frequency spectrum. However, as sensor technology evolves, a new challenge has emerged: thermal performance. Today, we analyze the sophisticated engineering balance between radar stealth and infrared management, and how the F-35 maintains its operational advantage in a multispectral environment. The geometry of radar management. Radar systems operate by emitting electromagnetic pulses and listening for the echo that bounces off an object. To counter this, the F-35 utilizes a two-pronged engineering strategy: geometry and material science. First, the external shape of the aircraft is designed with plan-form alignment. Notice how the leading edge and trailing edge of the wings and tail surfaces are set at identical angles. This ensures that any radar energy not absorbed is deflected away from the source at a precise, non-returning angle. Secondly, the aircraft is coated in advanced radar-absorbent materials, or RAM. These specialized polymers are engineered to trap electromagnetic energy and convert it into minute amounts of heat rather than allowing it to reflect. By integrating these systems, the F-35 presents a radar cross-section no larger than a small bird, significantly complicating long-range digital detection. The thermal challenge: thermal performance. While radar is an active detection method, infrared search and track systems are passive. They do not emit signals, they simply observe the heat energy radiated by all objects. In the cold environment of high-altitude flight, a jet engine is a massive thermal contrast. This is where thermal performance becomes critical.
every watt of energy produced by the F-135 engine must be managed. The core of the engine operates at temperatures high enough to melt standard metals. If this heat is not shielded, the aircraft becomes a bright beacon for long-wave infrared sensors, regardless of how stealthy its radar shape might be. Engineers face a difficult trade-off. High thrust requires high heat, but high heat increases the detection range of thermal sensors. Engineering the solution. To manage this thermal signature, the F-35 employs several groundbreaking engineering solutions. One of the most vital is high bypass cooling. Before the hot exhaust leaves the nozzle, it is shrouded by a layer of cooler bypass air. This masks the most intense heat and accelerates the cooling of the exhaust plume as it enters the atmosphere. Additionally, the F-35 uses its fuel as a primary heat sink. Before the fuel reaches the engine, it is circulated through the aircraft's electronics and hydraulic systems to absorb excess thermal energy, effectively recycling heat within the airframe. Furthermore, the design of the S-duct air intakes ensures that the spinning, hot compressor blades of the engine are never in a direct line of sight for incoming sensors. Every curve and every material choice is a calculated move to minimize the thermal footprint while maintaining peak aerodynamic performance. The multispectral future. The F-35 represents the pinnacle of modern signature management. It is a machine designed to operate at the edge of physical limits, balancing the requirements of radar deflection with the necessity of thermal suppression. As detection technology moves further into the multispectral realm, using both radio waves and light energy simultaneously, the role of the aerospace engineer becomes even more complex. The goal is no longer just to be stealthy, but to be digitally integrated and thermally optimized. Thank you for joining us for this technical analysis of modern aviation. If you enjoyed this deep dive into aerospace engineering, consider subscribing for more insights into the machines that define our era.
F-22 versus F-16, the ultimate comparison. 3 aircraft, 3 different philosophies, one question that has fascinated engineers, pilots, and aviation enthusiasts for nearly 2 decades. Which one is actually the best? But here's the catch. The answer is not as simple as you might think, because each of these machines was designed for a completely different job. And when you look under the skin, past the speed, the shapes, the numbers, you begin to realize that comparing them is like comparing a chess grandmaster, a sprinter, and a Swiss Army knife. In this video, we're going to break down the F-35 Lightning II, the F-22 Raptor, and the legendary F-16 Fighting Falcon. Not to declare a single winner, but to understand what makes each one unique. We'll talk about stealth, speed, technology, and the real-world roles they play in modern aviation. So strap in, because this is the ultimate comparison. 3 different worlds. Let's start with a quick introduction to each aircraft. First, the F-35 Lightning II. This is the newest member of the family. Sometimes called the Joint Strike Fighter, the F-35 was designed from the ground up to be a multi-role platform. That means it can perform many different types of missions, from gathering intelligence to supporting ground operations, all while being extremely difficult to detect. The F-35 is often described not as a traditional fighter, but as a flying supercomputer. Its most powerful feature isn't an engine or a gun, it's data. We'll get to that later. Next, the F-22 Raptor. If the F-35 is a Swiss Army knife, the F-22 is a scalpel. It was built for one primary purpose: air dominance. The Raptor is faster, more agile, and carries more fuel and systems dedicated to outperforming any other aircraft in the sky. The F-22 entered service in the early 2000s, and to this day, it is considered by many experts to be the most capable air-to-air platform ever built. But it's also expensive. So expensive that production stopped after less than 200 units. And finally, the F-16 Fighting Falcon, also known as the Viper by pilots who fly it. The F-16 is the old veteran. It first flew in the 1970s, over 50 years ago. But don't let its age fool you. The F-16 is still in active service with dozens of countries around the world. More than 4,000 have been built. It's lightweight, incredibly maneuverable, and relatively affordable. The F-16 proved that you don't need a huge, expensive machine to be effective. Sometimes simplicity and reliability win the day. So, 3 aircraft, 3 different eras, 3 different design philosophies. Now let's start comparing them where it really matters: stealth and design. Stealth and design, the art of not being seen. Stealth. It's the word you hear most often when people talk about modern military aviation, but what does it actually mean? In simple terms, stealth is the ability to reduce an aircraft's visibility to radar, infrared, and other detection systems. It's not about becoming invisible to the human eye. That's easy. It's about becoming invisible to the electronic eyes that scan the sky from hundreds of kilometers away. Think of it like this. When a radar station sends out a signal, that signal travels through the air until it hits something: a bird, a cloud, or an aircraft. Then a small part of that signal bounces back to the radar receiver. The stronger the return signal, the larger the object appears on the screen. A conventional aircraft, like an old airliner, reflects a huge amount of radar energy. It looks like a barn on the radar screen. A typical fighter from the 1980s looks more like a car. But a stealth aircraft, it can look as small as a golf ball, or even smaller. So, how do the F-35, F-22, and F-16 compare in this area? Let's start with the F-16, because it's not a stealth aircraft at all. The F-16 was designed in an era when stealth was not a priority. Engineers focused on aerodynamics, thrust-to-weight ratio, and cost-effectiveness. The F-16 has a traditional round air intake, vertical tail fins, and external stores, all of which reflect radar energy very well. That doesn't mean the F-16 is bad. It simply means that in a modern detection environment, the F-16 would be visible from a long distance. Its survival depends on speed, maneuverability, and electronic countermeasures, not on hiding. Now, the F-22 Raptor is a completely different story. The F-22 was the world's first operational stealth fighter designed for air dominance. Its shape was carefully engineered using something called planform alignment. All the leading edges of the wings, tails, and control surfaces are set at very specific angles so that radar waves bounce away from the source rather than back to it. The F-22 also uses radar-absorbent materials, or RAM, baked into its skin. These materials convert radar energy into tiny amounts of heat, which then dissipate. The result is an aircraft with an incredibly small radar cross-section, often compared to that of a marble. But the F-22 is not the stealth champion in this comparison. That title goes to the F-35. Why? Because the F-35 benefits from 20 more years of research and computer modeling. The F-35 takes the same plan-form alignment principles and refines them even further. Its surface is smoother, its edges are sharper, and its skin uses a new generation of durable fiber matte RAM that requires far less maintenance than older stealth coatings. But there's another layer: internal carriage. The F-35 was designed to carry all of its mission equipment, fuel, sensors, and internal stores inside the fuselage. There are no external fuel tanks or pods hanging off the wings when stealth is required. This keeps the aircraft's shape perfectly clean, with no protruding surfaces to reflect radar. The F-22 also carries its stores internally, but its external profile is slightly less refined than the F-35's. And the F-16? It carries everything externally, which is why it lights up on radar like a Christmas tree. So, in terms of stealth, the F-35 wins, followed closely by the F-22. The F-16 does not compete in this category because it was never designed to. But stealth is only one part of the story. Let's talk about speed and performance. Speed and performance. The need for speed. When most people think of fighter jets, they think of raw speed, afterburners, breaking the sound barrier, pulling high G turns. And in this category, the three aircraft are surprisingly different. Let's start with the numbers. The F-22 Raptor is the fastest of the three. It can reach speeds of over Mach 2.2. That's more than 2,300 kilometers per hour. And here's the incredible part. The F-22 can maintain supersonic speeds without using its afterburner, thanks to something called supercruise. Very few aircraft in the world can do that. The F-22's engines, two Pratt & Whitney F-119s, produce an enormous amount of thrust. Combined with its lightweight airframe and aerodynamic design, the Raptor can climb like a rocket and turn tighter than almost anything in the sky. Now, what about the F-35? The F-35 is powered by a single engine, the Pratt & Whitney F-135, which is actually the most powerful fighter engine ever built. It produces more thrust than the F-22's individual engines. But the F-35 is also heavier and has a different shape, optimized for stealth rather than pure speed. As a result, the F-35 has a top speed of around Mach 1.6, about 1,600 kilometers per hour. That's slower than the F-22 and even slightly slower than some versions of the F-16. But here's the thing. Speed is not the F-35's primary advantage. The F-35 is designed to be a first-look, first-shot platform, not a drag racer. It doesn't need to be the fastest because it can see and track other aircraft long before they see it. And finally, the F-16. The F-16 is surprisingly fast for its size and age. Depending on the model, it can reach Mach 2.0 or slightly higher. But the real magic of the F-16 is not top speed, it's maneuverability. The F-16 was the first production fighter to use a fly-by-wire system. Instead of mechanical linkages between the stick and the control surfaces, the pilot's inputs go to a computer, which then moves the surfaces. This allowed engineers to design an inherently unstable aircraft that could turn incredibly fast. Pilots often say the F-16 feels like it's part of your body. It responds instantly. It can pull up to 9 Gs, meaning 9 times the force of gravity. That's physically demanding for the pilot, but it makes the F-16 one of the most agile fighters ever built. So, in terms of raw performance, F-22 is the fastest and most agile overall. F-16 is incredibly agile, especially for its age and cost. F-35 is slower but still highly capable, and its performance is more than adequate for its mission profile. But speed and agility are becoming less important in modern aviation. What really matters now is technology. Technology and innovation, the flying information platform. If the F-16 represents the past and the F-22 represents a bridge between past and future, the F-35 represents a complete rethinking of what an aircraft should be. Let me explain. The F-16 was designed in the 1970s. Its cockpit is filled with analog gauges, mechanical switches, and a small radar screen. Over the years, the F-16 has been upgraded with digital displays and modern sensors, but at its core, it's still a pilot-oriented machine. The pilot flies the plane and the systems help. The F-22 took a big step forward. Its cockpit is all glass, large color displays, advanced radar, and a sophisticated electronic warfare system. The F-22 was the first fighter to integrate sensors so that the pilot sees a fused picture of the environment. But the F-22's technology, while groundbreaking in the 1990s, is now nearly 30 years old. Then comes the F-35, and this is where things get really interesting. The F-35 is often described as a flying information platform, not just a fighter jet. Its most important capability is not speed, not stealth, not even its engine. It's data. The F-35 is equipped with a sensor suite called the AN/APG-81AESS radar, the Distributed Aperture System (DAS), and the Electro-Optical Targeting System (EOTS). These sensors collect enormous amounts of information from the environment: radar signals, infrared heat, visual imagery, and electronic emissions. But here's the magic. The F-35's computers automatically fuse all that data into a single intuitive picture. The pilot doesn't have to look at 5 different screens and mentally combine the information. The aircraft does it for them. And that picture is presented through the pilot's helmet, a $400,000 piece of engineering that projects flight data, targeting information, and video directly onto the visor. The helmet is connected to 6 infrared cameras mounted around the aircraft. Together, they create a 360-degree view of the world. The pilot can literally look down through the floor of the cockpit and see the ground below. They can look behind them without turning the aircraft. It's like having X-ray vision. But the F-35's real power goes beyond the individual aircraft. The F-35 was designed to share data with other platforms, other F-35s, older aircraft, ships, and ground stations. This creates a shared picture of the operational environment. What one F-35 sees, the entire team sees. That is revolutionary. It means that an F-35 can fly into a complex environment, silently map every signal source, and then share that information with an F-16 flying safely at a distance. The F-16 suddenly has the same awareness as the F-35, without having the same stealth or sensors. So, in terms of technology, the F-35 is in a league of its own. The F-22 is still very capable, but aging. The F-16 has been upgraded many times, but it cannot match the sensor fusion and data sharing capabilities of the 5th-generation aircraft. Now let's look at how these aircraft are actually used in the real world. Real-world application. Different tools for different jobs. You might be wondering, if the F-35 is so advanced, why do countries still fly F-16s? And why did the US stop making F-22s? The answer comes down to 3 things: cost, mission requirements, and numbers. Let's start with the F-22 Raptor. The F-22 is an extraordinary machine, but it is also extraordinarily expensive. Each F-22 cost around $150 million, and that's just the aircraft, not including development, maintenance, or training. Because of its high cost and the fact that the Cold War had ended, the US government decided to stop F-22 production after 195 aircraft. Today, the F-22 fleet is relatively small, and it is used primarily for specific high-end defense scenarios where its unique combination of speed, stealth, and sensors is needed. The F-22 does not carry as many external systems for ground operations. It was designed to dominate the air environment, and that is what it does best. But it is not as flexible as the F-35. Now, The F-35 was designed to be the opposite, flexible and affordable enough to be built in large numbers. There are three main versions of the F-35. The F-35A for conventional runways, the F-35B with short takeoff and vertical landing capability, perfect for small ships or damaged runways, and the F-35C for aircraft carriers. More than 900 F-35s have been built so far, and the total planned production is over 3,000. That makes the F-35 a common platform for many countries, including the United States, the United Kingdom, Australia, Japan, and others. The F-35 is used for a wide variety of missions, gathering intelligence, supporting ground forces, patrolling airspace, and operating in complex electronic environments. Its ability to share data makes it a force multiplier. It makes everyone around it more effective. And then, there's the F-16 Fighting Falcon. The F-16 is the workhorse. It is relatively cheap, about $20 to $30 million for a modernized version. It is easy to maintain, it can operate from rough runways, and it has been continuously upgraded for over 50 years. More than 25 countries still fly the F-16. Some have upgraded their F-16s with new radars, new cockpits, and even some stealth features like conformal fuel tanks. The F-16 cannot match the stealth or sensors of the F-35, but it doesn't have to. In many defense scenarios, the F-16 is good enough, and when you need to patrol large areas, train new pilots, or operate on a budget, the F-16 is the smart choice. So, in real-world application, F-22 is a specialized low-volume platform for high-end air dominance. F-35 is a high-volume multi-role platform for the future. F-16 is the reliable, cost-effective workhorse that will likely fly for another 20 years. But now, the question you've been waiting for.
Final verdict. Which aircraft is the best? Which one is the best? The honest answer is, it depends entirely on what you need. If you ask a pilot who values raw performance and agility above all else, they might say the F-22 Raptor is the best. Nothing else can climb faster, turn tighter, or accelerate like the Raptor. It is the king of the air environment, a masterpiece of aerodynamics and engine design. But the F-22 is also rare, expensive, and less flexible than its younger sibling. If you ask a mission planner who needs to cover many different types of operations, from intelligence gathering to supporting ground teams, they will almost certainly choose the F-35 Lightning II. The F-35 is not the fastest and it's not the most agile, but it sees everything, it knows everything, and it shares everything. The F-35 represents a fundamental shift in aviation. It's not about how fast you can fly. It's about how much information you can collect, process, and distribute. In that sense, the F-35 is not just a fighter, it's a node in a network, and networks are the future. And if you ask a defense minister who has to balance a budget, train dozens of pilots, and protect a large airspace, they might say the F-16 Fighting Falcon is the best, because you can buy 10 F-16s for the price of one F-22. You can upgrade them over time, you can operate them from almost anywhere, and they have a proven track record spanning half a century. The F-16 is the ultimate example of good enough being truly great. So here is the final verdict. For pure performance and air dominance, F-22 Raptor. For advanced technology, data integration, and future readiness, F-35 Lightning II. For cost-effectiveness, versatility, and proven reliability, F-16 Fighting Falcon. But if we had to choose one aircraft that represents the direction aviation is heading, it has to be the F-35. Because the era of the lone fighter dogfighting in the sky is fading. The future belongs to connected systems, sensor fusion, and shared awareness. And no aircraft does that better than the F-35. The bigger picture. So after all of this, what have we learned? We learned that comparing aircraft is not about declaring a winner. It's about understanding design choices, trade-offs, and mission requirements. The F-22 was built to be the ultimate performer, and it succeeded.
The F-16 was built to be affordable and effective, and it exceeded all expectations. The F-35 was built to be the most advanced information platform in the sky, and it is redefining what an aircraft can do. Each of these machines represents a moment in aviation history, and together they show us how far engineering has come and where it might go next. What will the next generation look like? Will we see unmanned systems taking over? Will artificial intelligence fly alongside human pilots? Will aircraft become even more invisible, even more connected? Those are questions for another video. For now, we hope you enjoyed this ultimate comparison. If you did, please consider subscribing and hitting the notification bell, because we are constantly exploring the world's most amazing technology. And let us know in the comments, which aircraft is your favorite and why? We read every single comment. Thanks for watching, and remember, the sky is not the limit, it's just the beginning. What if I told you that the most powerful airborne radar in the world, the one they call the eyes of the entire Air Force, could become blind? And that its main vulnerability is not in its engines or electronics, but in a simple law of physics you learned in school. Today, we are breaking down the E-3 Sentry AWACS, why it is called the eye in the sky, how it works, and how it can still be detected. Subscribe to the channel if you want to see the real physics behind military technology, not just loud headlines. And let's begin. What is AWACS and why it matters? AWACS is not just an aircraft, it is a full airborne command station, airborne warning and control system, literally a flying control tower. Imagine an airport control tower in the world's largest airport. Now lift that tower to an altitude of 9 kilometers, make it mobile, and give it the ability to see not just 100 kilometers, but 400 kilometers in all directions. That is the E-3 Sentry. This aircraft was designed back in the 1970s, but it remains a key element of air power today. Why? Because without it, fighters are like boxers with blindfolds. They can throw punches, but they cannot see where the danger is coming from. The E-3 takes on the role of eyes. Its famous rotating dome above the fuselage is not a communication antenna, it is a passive electronically scanned array radar. It rotates at 6 revolutions per minute and scans the space around it. How the E-3 radar works. Let us go a bit deeper. That dome is not just round. Its diameter is 9.5 meters, its thickness is nearly 2 meters. Inside is an antenna that emits radio waves in the range of 1.5 to 2 centimeters. This is the so-called EF band, or S band in oldie terminology. These waves reflect off aircraft, off the ground, off clouds, and the computer on board the E-3 filters out noise and shows operators a clear picture: who is flying where, at what altitude, at what speed, and most importantly, friend or foe. The detection range for large targets like bombers reaches 600 kilometers. It sees fighters from 350 to 400 kilometers, and cruise missiles flying low over the ground roughly 250 kilometers. But there is one detail, and that detail is the key to answering the question, how can AWACS be detected? The main vulnerability: emission. AWACS is not a passive listener, it actively emits, very powerfully. Its radar is not a flashlight, but a searchlight that reaches hundreds of kilometers. And any modern electronic intelligence aircraft, any ground-based passive direction finding station can detect that emission. More than that, they can determine the direction, power, and even the type of radar. Imagine you are in a dark room shining a powerful flashlight. Yes, you see everything around you, but anyone outside that room also sees your light and knows where you are standing. This is the main physical problem of all airborne early warning and control aircraft. The more powerful your radar, the better you see targets, but the more visible you become to passive systems. And here is another important point. Modern passive location systems can not only detect the signal, they can identify the aircraft by its radar fingerprint. Because every radar has unique modulation characteristics, frequencies, pulse durations. And when you know which aircraft is seeing you, you can start taking countermeasures. What about stealth technology? People often ask, why is AWACS itself not built with stealth technology? Then it would be harder to detect. The answer is simple. Stealth and a powerful radar do not mix well. For an aircraft to have low radar visibility, its shape must be special. No external stores, flat surfaces, special coatings. And that huge rotating dome is a perfect reflector. It cancels out any attempt to reduce radar signature. Moreover, the E-3 is an aircraft from the early 80s. Its platform is the Boeing 707. That is a passenger airliner that was never designed with stealth in mind. But even if engineers created a fully low observable AWACS aircraft, it would still emit its radar signal, and that signal would still be visible to passive systems. Therefore, AWACS will never be invisible. Its job is not to hide, its job is to see first and control the air battle from a safe distance. How adversaries can detect AWACS. Now let us talk about how detection systems can determine the location of such an aircraft. We will not discuss specific incidents or countries, only physics and technology. The first method is passive direction finding, already mentioned. 2 or 3 ground stations placed at a distance from each other measure the time difference of arrival of the AWACS radar signal and calculate its position. This works even if the aircraft does not see you, for example, because of terrain masking. The second method is using low-frequency radars. Typical fighter radars and air defense systems operate in the centimeter band, but there are also meter wave and decimeter wave early warning radars. They have low accuracy and cannot guide a missile, but they are excellent at seeing large targets, and the E-3 is a very large target. Its wingspan is 44 meters, length 46 meters. That is like a 3-story house with wings. Such radars are not affected by stealth coatings. They see the aircraft not by reflection from the skin, but by resonance on structural elements, wingtips, tail, antennas. And they can detect the E-3 from 200 to 300 kilometers away. The third method is space-based reconnaissance. Electronic intelligence satellites in low orbits can detect radar emissions anywhere in the world, and if AWACS turns on its radar, its signal can be picked up by a satellite. But it is important to understand, detection is not the same as targeting. To guide a missile to a target, precise tracking is required, and that is much more difficult. What this means for the future of AWACS. So we have established that the E-3 Sentry was never invisible and never will be. Its main strength is detection range and command capability. Its main weakness is its own emission. So, what are designers doing? The newest next-generation AWACS aircraft replacing the E-3 is called the E-7 Wedgetail. It is based on the Boeing 737. It has a different antenna, not a rotating dome, but a fixed electronically scanned array, ESA. Such radars can change beam shape, switch between modes, and, crucially, use low probability of intercept techniques. They can operate in modes where the signal is spread across a wide frequency band, making it much harder for passive systems to detect. But the emission problem cannot be fully solved. As long as the radar is working, it reveals itself. So the tactical solution remains the same. Turn on the radar only when necessary and change position after each session. This is the reality of 21st century aviation. nothing is completely invisible. There is only smart risk management, good tactics, and understanding of physics. If you want to understand military aviation not at the level of loud headlines, but at the level of engineering and physical principles, subscribe to this channel. We do not scare you with breaking news. We show you how things actually work. Like this video if you want the next one about the E-7 Wedgetail, a comparison of 2 generations of flying eyes. And I will say goodbye. See you next time in the sky, which we study from the ground. Inside the E-3 Sentry AWACS, the aircraft that sees everything. What if one aircraft could see hundreds of kilometers in every direction, track dozens of targets at once, and coordinate everything happening in the sky? This is not science fiction. This is the E-3 Sentry. Often called the eyes in the sky, this aircraft is one of the most important platforms in modern aviation. And yet, most people have never truly understood how it works. Let's change that. The E-3 Sentry is an airborne warning and control system aircraft, also known as AWACS. Built on a modified Boeing 707 airframe, the E-3 combines long-range radar, advanced communication systems, and mission control capabilities into a single flying platform. Its purpose is simple, but incredibly powerful: to see everything and help others act faster and smarter. Unlike traditional aircraft, the E-3 is not designed for speed or maneuverability. It is designed for awareness. And in modern aviation, awareness is everything. The radar dome, how it sees everything. The most recognizable feature of the E-3 Sentry is the large rotating dome mounted above the fuselage. This dome, called a rotodome, houses a powerful radar system. As it rotates, it scans the surrounding airspace in a full 360-degree circle. This allows the aircraft to detect and track objects at extremely long distances, often hundreds of kilometers away. But what makes this radar truly special is not just its range, it's its ability to detect multiple targets at the same time. Instead of focusing on a single object, the system continuously monitors the entire airspace, identifying aircraft, tracking movement, and building a complete picture of what's happening in real time. This is what gives the E-3 its nickname, the aircraft that sees everything. Inside the aircraft, a flying command center. Step inside the E-3 and you'll find something very different from a typical cockpit. Behind the flight crew is a large mission area filled with consoles, screens, and operators. Each operator has a specific role: tracking targets, analyzing data, managing communications, and coordinating with other platforms. Together, they form a flying command center. Instead of just flying the aircraft, the crew is actively managing the entire airspace around them. They can guide other aircraft, provide situational awareness, and ensure that everyone involved has the information they need. This level of coordination is what makes the E-3 so valuable. It doesn't just observe, it organizes. Data, communication, and control. The E-3 is not only about radar, it is also about communication. Using advanced data links and communication systems, the aircraft can share information with multiple platforms at the same time. This includes fighter aircraft, ground stations, and naval units. The result is a shared picture of the environment, a real-time understanding of what is happening across a large area. Instead of each unit working independently, everything becomes connected. This dramatically improves efficiency and coordination. The E-3 acts as the central node, collecting information, processing it, and distributing it where it is needed most. In many ways, it is less like an aircraft and more like a flying network. Endurance and global operations. Another key strength of the E-3 Sentry is its endurance. With aerial refueling, it can remain airborne for extended periods, providing continuous coverage over a region. This makes it ideal for long-duration operations where consistent awareness is critical. The aircraft has been used by multiple countries and organizations, including the United States and NATO. Its flexibility allows it to operate in a wide range of environments, from large-scale exercises to routine monitoring missions. No matter the scenario, its role remains the same: maintain awareness, provide coordination, support decision-making. Technology evolution. Although the E-3 Sentry was first introduced decades ago, it has undergone continuous upgrades. Modern versions include improved radar capabilities, enhanced processing power, and updated communication systems. These upgrades ensure that the aircraft remains relevant in an ever-changing technological landscape. As new systems are developed, the role of airborne early warning continues to evolve. But the core idea remains unchanged. Information is the most valuable asset, and the E-3 is built to collect, process, and distribute that information as efficiently as possible. Why it still matters today? In today's world where technology is advancing rapidly, the ability to understand complex environments is more important than ever. Aircraft like the E-3 Sentry provide that understanding. They allow operators to see beyond the horizon, anticipate changes, and respond effectively. While newer platforms are being developed, the E-3 remains a key part of modern aviation infrastructure. Its combination of radar, communication, and coordination capabilities makes it a unique and powerful system. It is not defined by speed or agility. It is defined by intelligence. So, what makes the E-3 Sentry so important? It's not just the radar, it's not just the technology, it's the ability to bring everything together, to see the big picture, to understand it instantly, and to share it with others. The E-3 is more than an aircraft, it is the eyes of the sky. And in a world driven by information, that makes all the difference. AWACS versus F-35. Can a giant radar actually see a stealth jet? What if I told you that a massive AWACS aircraft, based on a 50-year-old Boeing 707, can actually detect one of the most advanced stealth fighters ever built? And what if I told you that even when it does, it still can't reliably engage it? That's the real story. Not stealth is dead, not AWACS is useless, but a high-stakes contest defined by physics, geometry, and time. Let's start with the F-35. The F-35 Lightning II was never designed to be invisible. Invisibility is a myth. Stealth is control. Control over when you are seen, from where you are seen, and how clearly you are seen. At its core, stealth is about reducing detection range and degrading tracking quality. The F-35 achieves this through two primary mechanisms. First, shape. Every edge is aligned. Every surface is angled with intent. Incoming radar waves are redirected away from the source rather than reflected back toward it. Second, materials. Radar-absorbent coatings convert part of the incoming energy into heat, reducing the strength of the return signal. The result is a drastically reduced radar cross-section. But here is the critical point. Radar cross-section is not a fixed value. It is not a constant. It changes with aspect angle, radar frequency, and the surrounding environment. And this is exactly where most people get it wrong. Now consider AWACS. AWACS stands for Airborne Warning and Control System. The Boeing E-3 Sentry is the most recognizable example. A large aircraft with a rotating radar dome scanning vast areas of airspace from high altitude. But this is not a fighter radar. It is not designed for precision targeting. It is designed for persistence, wide area surveillance, continuous coverage, long-range detection. It looks down at the battle space, and that changes everything. Most stealth shaping is optimized against forward-facing threats, fighter radars, ground-based fire control systems. Those systems illuminate the aircraft from roughly the same altitude and from predictable angles. But AWACS observes from above. Different geometry, different scattering behavior. Surfaces that deflect energy away from a frontal radar may not behave the same way when illuminated from the top or from oblique angles. As a result, the effective radar cross-section of the F-35 can increase from certain aspects. But larger does not mean large. It means less small. Against an X-band fighter radar, the F-35 is often compared to a marble. Against a lower frequency AWACS radar, it may behave more like a baseball, still extremely small. But no longer at the extreme edge of detectability. Now consider frequency. Fighter radars typically operate in higher frequency bands, such as X-band and Ku-band. Short wavelengths, high resolution, precise tracking. Stealth is heavily optimized against these frequencies. AWACS radars often operate in lower frequency bands, such as L-band or S-band, longer wavelengths. And this is where stealth begins to lose some of its advantage. Long wavelengths are less sensitive to fine geometric shaping. They interact with the aircraft as a larger structure rather than as a collection of carefully aligned edges. Under certain conditions, this allows low-frequency radar to detect the presence of an object that would be extremely difficult to observe at higher frequencies. But detection is not tracking, and tracking is not targeting. This is the distinction that defines everything. An AWACS system may register a weak, unstable return, a signal that appears briefly, then fades. A contact that does not behave like a conventional aircraft. The operator sees an anomaly, but an anomaly is not a solution. To engage a target, you need a continuous, high-confidence track. You need velocity, direction, altitude. You need to predict where the target will be seconds into the future. AWACS does not provide that level of precision. It provides awareness, not engagement. So yes, under certain conditions, AWACS can detect something, but detection alone does not create a firing solution. Now introduce electronic warfare. The F-35 is not just a passive, low observable platform. It actively shapes the electromagnetic environment. It can degrade incoming radar signals. It can inject false information. It can manipulate what the radar system believes it is seeing. This is not speculation. This is electromagnetic interaction governed by physics. Radar transmits energy and interprets reflections. Electronic warfare introduces additional energy to disrupt that interpretation. The result is uncertainty, and uncertainty is the single greatest barrier to engagement. Now make this real. Consider 3 scenarios. Scenario 1. The F-35 is operating at altitude, flying a predictable path with weapons bays open. Its radar cross-section increases. For a brief moment, it becomes more visible.
AWACS detects a return at long range, but the F-35 is not blind. Its sensors detect the AWACS emissions. The pilot adjusts heading, closes the bays, activates electronic countermeasures. The detection degrades, then disappears. Scenario 2. The F-35 operates at low altitude. Terrain masking becomes dominant. AWACS is forced to look down through ground clutter. The radar environment becomes saturated with noise. The aircraft's already small signature blends into that environment. No reliable detection. Scenario 3. A networked environment. Multiple radars, multiple frequencies, sensor fusion. One system detects a weak return, another sees nothing. A third detects a different signature. Data is combined. Algorithms attempt to construct a usable track. Sometimes they succeed. Often they do not. And now the system is estimating. The commander is making decisions based on incomplete information. Time passes. The F-35 moves. The opportunity collapses. This is modern air combat. Not binary, not deterministic. A continuous contest between detection and deception. So here is the real answer. Can AWACS detect the F-35? Under specific conditions, yes. At certain angles, at certain ranges, with certain frequencies. But detection is not victory. Detection is information. And information only matters if it can be converted into action fast enough. That is the real contest. Not stealth versus radar, but certainty versus time. The F-35 is engineered to exploit that gap. It delays detection. It degrades tracking. It injects uncertainty. It operates with its own sensor fusion, building a coherent picture while revealing as little as possible. AWACS is designed to counter this. It expands coverage. It integrates data. It increases the probability of detection. But it has limitations. It is large. It is slow. It is highly visible. In a contested environment, it becomes a priority target. So this is not a one-sided interaction. It is a system-level competition. Each side adapting, each side compensating, each side operating under constraints. Now consider real-world analysis. In multiple simulated scenarios, low observable aircraft produced intermittent detections on AWACS-class systems. Detection windows lasted seconds, 5 to 15 seconds, not minutes. Seconds. That is not enough to establish a stable engagement chain. By the time a weapon could be guided, the conditions that enabled detection have already changed. Aspect angle shifts, altitude changes, electronic warfare activates. The track collapses. This is why stealth remains effective. Not because it eliminates detection, but because it compresses the timeline. And in air combat, time is decisive. A few seconds can determine whether an aircraft is engaged or survives. So what does this mean? It means abandoning absolute thinking. Stealth is not invisibility. Radar is not omniscience. Both are tools within a dynamic system, and that system is evolving. Radar systems are becoming more adaptive. Signal processing is becoming more intelligent. Stealth materials and shaping continue to improve. Electronic warfare is becoming more sophisticated. This is not a solved problem. It is an ongoing competition. a continuous cycle of measure and countermeasure. Understanding that cycle is the key, not isolated claims, not simplified conclusions, but the interaction between systems operating under uncertainty. So when someone says AWACS can detect the F-35, the real questions are different. For how long, with what confidence, and what happens next? Because those answers determine the outcome. If you want to understand how modern air combat actually works, based on physics and system behavior, not simplified explanations, subscribe. And in the next video, we go one step further. What actually happens when a modern missile tries to hit a stealth aircraft? Thank you for watching. I'll see you in the next breakdown. How the F-15E Strike Eagle gets detected. Real engineering breakdown. What if I told you that one of the most powerful fighter jets ever built is not trying to be invisible? The F-15E Strike Eagle is fast, extremely powerful, capable of carrying massive payloads, but when it comes to radar, it was never designed to hide. So the real question is not, can it be detected? The real question is, how does it survive in a world where everything can see it? That's exactly what we're breaking down today. Real engineering, real physics. No hype, no myths, just how it actually works. If you enjoy this kind of content, subscribe to the channel. This is where aviation gets explained properly. Let's start simple. What does detection actually mean? Most people imagine something dramatic, a warning alarm, a missile lock, instant danger. But in reality, detection is just physics. A radar sends out electromagnetic waves. Those waves travel through the air, hit an object, and a small portion reflects back. That reflected signal is what the radar sees. That's it. So detection is not a special event, it's just energy bouncing off a surface. Now here's where the F-15E comes in. The Strike Eagle was designed for power and versatility, not stealth. Look at its structure: large wings, twin vertical tails, external weapons mounted under the wings, visible engine intakes. All of this reflects radar energy extremely well. Which means one thing: the F-15E has a large radar cross-section. In simple terms, it looks big on radar. Compared to stealth aircraft, it's not even close. But here's the part most people completely misunderstand. Being visible does not mean being vulnerable. Modern air combat is not about invisibility, it's about information. Let's break that down. Detection happens in stages. First, a radar sees a small signal return, just a dot, no details. Second, tracking. The radar follows that dot over time to calculate speed and direction. Third, identification. Is it friendly? Unknown? Something else? And only after that comes engagement. Each step takes time. Each step can fail. And that's exactly where the F-15E operates. So how does it survive? Let's go step by step. 1. Speed and positioning. The F-15E is incredibly fast. It can reach speeds over Mach 2. It can climb rapidly. It can reposition faster than most systems can react. So even if a radar detects it, that information becomes outdated very quickly. Position is everything. 2. Electronic warfare. This is where things get very interesting. The F-15E is equipped with advanced electronic warfare systems. It doesn't just fly, it actively interacts with the electromagnetic environment. It can detect radar signals, identify their type, and respond in real time. It can jam signals, distort tracking data, or overwhelm radar receivers with noise. So even if a radar sees something, it may not see it clearly. 3. Radar warning systems. Inside the cockpit, the pilot is not blind. The aircraft constantly monitors the environment. If a radar is scanning, the system knows. If a radar locks on, the system knows instantly. Different signals produce different alerts, which means the pilot always has situational awareness. And that changes everything, because reaction time becomes the key advantage. 4. Countermeasures. The F-15E carries multiple defensive tools. Chaff, small metallic strips that confuse radar. Flares, used to mislead infrared tracking systems. These are simple, but extremely effective. They don't make the aircraft invisible, but they break the tracking process. And remember, tracking is required before engagement.
5. Networked awareness. Here's something many people overlook. The F-15E is not operating alone. It is part of a larger system. Data is shared between aircraft, between airborne systems, between ground and naval platforms. So while one system may detect the aircraft already knows about that system before anything escalates. That's the real advantage. Now let's talk about something important. Why not just make everything stealth? Why not eliminate detection completely? Because stealth comes with trade-offs, serious ones. Complex shapes, expensive materials, limited payload capacity, and higher maintenance requirements. The F-15E was designed with a different philosophy. Instead of hiding, it dominates through capability. More weapons, more range, more flexibility. And that's why it still matters today, even in a world full of advanced radar systems. Now let's talk about another detection method, infrared, heat. The F-15E has two powerful engines. They generate a lot of heat. Infrared sensors can detect that heat signature from long distances. So again, it's not invisible. But just like radar, detection is only the first step. Infrared tracking can be disrupted. Flares can create false targets. Environmental conditions can reduce visibility. And pilot decisions matter more than anything. Let's bring this together. The biggest myth in aviation is simple. If you are detected, you are done. That is completely false. Detection is only the beginning of a long chain, and every part of that chain can be interrupted. The F-15E was never meant to disappear. It was built to operate in complex environments, to adapt, to respond, to survive. And it does that extremely well. So the next time you hear someone say, "This aircraft is not stealth," ask a better question. Does it need to be? Because in real engineering, there is no perfect solution, only trade-offs. Let me summarize everything in a simple way. 1. The F-15E is easy to detect compared to stealth aircraft. 2. Detection does not equal vulnerability. 3. Survival comes from speed, awareness, and electronic warfare. 4. Modern combat is about information, not invisibility. 5. The F-15E remains relevant because of its versatility and power. Now I want to hear your opinion. Do you think stealth is the future? Or do you think powerful non-stealth aircraft still have a major role? Write your thoughts in the comments. I read every single one. And if you want real engineering breakdowns like this, no hype, no noise, just how things actually work, subscribe to the channel,
because the next video will go even deeper. Thanks for watching, and I'll see you in the next breakdown. F-15E Strike Eagle. How a non-stealth jet survives modern radar. The F-15E Strike Eagle is not invisible. Every modern radar system can detect it. Every infrared sensor can track it. Every advanced air defense network can see it coming. And yet, it continues to operate in some of the most dangerous and contested airspace in the world. So how does a fully visible fighter jet survive in an era dominated by stealth technology? And why hasn't it been replaced completely by aircraft designed to avoid detection? Let's start with the biggest misconception. Detection does not equal destruction. Being seen does not automatically mean being shot down. The F-15E Strike Eagle proves that reality is far more complex. Here is the truth. The aircraft was never designed to be stealth. Unlike newer platforms, it does not rely on shaping to deflect radar waves. It carries external weapons that increase its radar signature. It is powered by engines that generate significant heat. On paper, it should be one of the easiest aircraft to detect, and in many ways, it is. Modern radar systems can identify large aircraft shapes from long distances. They use multiple frequency bands to build a more complete picture of the sky. Low-frequency radar can detect the presence of an aircraft, even if it is optimized for stealth. High-frequency radar provides more precise tracking and targeting data. The F-15E appears clearly in both. It reflects radar energy rather than dispersing it. So detection is not the challenge. Tracking is not the challenge. Even engagement is not necessarily the challenge. Now, here is what most people get wrong. Modern air defense systems are not a single radar and a single missile. They are complex, layered networks. One system detects, another confirms, another tracks, another launches. All of this is connected through data networks that share information in real time. Long-range radar systems monitor large areas. Medium-range systems provide tracking and targeting. Short-range systems protect key assets. But radar is only part of the story. Infrared sensors play a critical role. These systems detect heat instead of reflected radio waves. Jet engines produce intense thermal signatures, especially under high thrust conditions. The F-15E has two powerful Pratt & Whitney engines. Each generates up to 29,000 pounds of thrust. That heat is visible from dozens of kilometers away. So again, detection is not the limiting factor. The aircraft can be seen, it can be tracked, and it can be targeted. Yet survival still happens. This is where the concept of survivability becomes critical. Survivability is not about avoiding detection entirely. It is about managing risk across multiple stages of engagement. The F-15E was designed with this philosophy in mind. Let me give you a concrete number. The F-15E has a radar cross-section, or RCS, of roughly 10 to 15 square meters. That is about the size of a large truck. A stealth fighter, like the F-35, has an RCS of approximately 0.001 square meters. That is closer to a marble. So the F-15E can appear 10,000 times larger on radar than an F-35. That sounds terrible. But here's the counterintuitive part. The F-15E does not try to hide. It relies on a combination of speed, altitude, electronic warfare, and coordination. Speed reduces exposure time. If an F-15E flies at Mach 1.2 through a threat zone, it covers 400 meters per second. The faster it moves, the less time enemy systems have to detect, track, and engage. Altitude also changes the game. Operating at different altitudes affects how radar waves interact with the aircraft. Low altitude uses terrain masking. High altitude increases detection range, but also allows faster response. Electronic warfare is one of the most important factors. The F-15E is equipped with systems designed to interfere with enemy radar. This includes jamming, which introduces noise into radar systems, and deception, which creates false targets or alters the perceived position of the aircraft. These systems do not make the aircraft invisible, but they make it harder to track accurately. And in modern air combat, accuracy is everything. A missile does not need to know that something exists. It needs precise targeting data to intercept it. Even small errors can result in a miss. Here's a real-world example. During operations in the Middle East, an F-15E crew detected an incoming surface-to-air missile launch. They did not turn invisible. They deployed chaff to confuse radar. They released flares to distract infrared seekers, and they executed a 7G turn. The missile missed by approximately 50 meters. Detection did not kill them. Physics and countermeasures did. Decoys add another layer of protection. Chaff consists of tiny aluminum or zinc fibers. When released, they create a cloud of false radar returns. Flares burn at temperatures higher than the aircraft engine. They pull heat-seeking missiles away from the real target. These countermeasures create uncertainty for incoming threats. They force the system to make decisions under imperfect information, and that increases the chance of survival. But the most important factor is not the aircraft itself. It is the network it operates within. The F-15E is rarely alone. It is part of a larger system that includes other aircraft, support platforms, and ground-based assets. Airborne early warning systems like AWACS provide a wide area view of the battlefield. They detect threats at long distances and share that information with other units. This allows the F-15E to adjust its path before entering the most dangerous zones. Electronic warfare aircraft can degrade or neutralize hostile radar coverage. They interfere with radar functionality and communication networks, reducing the effectiveness of the entire defense structure. Fighter escorts provide protection against enemy aircraft. They engage threats before they reach the strike platform. All of this creates a layered offensive system that mirrors the layered defensive system. Instead of one aircraft facing one defense system, it becomes a network versus a network. And in that environment, detection is only one part of the equation. Timing becomes critical. Operations are planned to exploit gaps in coverage. Routes are selected to minimize exposure. Attacks are coordinated to overwhelm defenses. Multiple assets may engage simultaneously, forcing the defense system to divide its attention. The F-15E is also designed for flexibility. It can carry a wide range of weapons. It can adapt to different mission profiles. Standoff weapons enable engagement from outside the most dangerous zones. Instead of flying directly over heavily defended areas, the aircraft can launch from a distance. Some air-to-surface missiles have ranges exceeding 100 kilometers. That keeps the F-15E outside short-range air defense bubbles. Another factor is payload capacity. The F-15E can carry up to 23,000 pounds of ordnance. That is roughly 10 tons. This means fewer aircraft may be required for certain missions, reducing overall exposure. It also means each sortie can deliver substantial impact. So why hasn't stealth completely replaced non-stealth aircraft? Because stealth has trade-offs. Internal weapon bays limit payload. Radar-absorbent materials require careful maintenance. Cost per flight hour is significantly higher. The F-35 costs approximately $40,000 per flight hour. The F-15E costs around $25,000. For missions that do not require penetrating the most advanced air defenses, the F-15E makes economic sense. Modern warfare is evolving rapidly. New technologies are constantly changing the balance. Advanced radar systems are becoming more capable. They use multiple frequencies. They integrate data from multiple sources. They apply advanced processing techniques. Infrared systems are improving as well. They are becoming more sensitive, more accurate, and more resistant to countermeasures. Artificial intelligence is beginning to play a role. It can process large amounts of sensor data, identify patterns, improve tracking. All of this makes detection more reliable, but it also makes the environment more complex because the same technologies can be used on both sides. Electronic warfare systems are becoming more advanced. They can adapt in real time. They can respond to changing conditions. They can target specific threats. Networked operations are becoming the standard. Data is shared across platforms. Decisions are made faster. Responses are coordinated. This creates a dynamic environment where advantages are constantly shifting. In this context, the idea of a single dominant technology becomes less relevant. There is no perfect solution. Every system has strengths and weaknesses. Stealth reduces visibility, but it often comes with trade-offs in payload or cost. Non-stealth platforms are more visible, but they can offer greater flexibility and capacity. The F-15E continues to operate because it fits into this evolving system. It is not trying to be invisible. It is designed to be effective. It leverages speed, coordination, electronic warfare, and strategic planning to operate in environments that appear extremely dangerous. This is why the concept of detection must be understood differently. Being detected does not mean being defeated. It means entering a complex interaction between multiple systems, where outcomes depend on many variables: technology, tactics, timing, coordination. All of these factors interact in ways that are difficult to predict. And that is what defines modern air combat. It is not a simple equation. It is a constantly evolving system, where advantages are temporary and adaptation is essential. The F-15E Strike Eagle is a product of this reality. It does not rely on invisibility. It relies on integration. It operates as part of a larger network. It uses multiple layers of protection, and it continues to prove that survivability is not about avoiding detection. It is about operating effectively within a complex and contested environment. As new technologies emerge, this balance will continue to shift. Future systems will become more advanced, detection will improve, tracking will improve, weapons will become more capable, but countermeasures will evolve as well. New forms of electronic warfare will be developed, new tactics will emerge, new platforms will be designed. Each generation will respond to the challenges of the previous one, and the cycle will continue. This is what makes modern military aviation so complex and so dynamic. It is not defined by a single breakthrough, but by continuous adaptation. The F-15E Strike Eagle remains relevant not because it is invisible, but because it is part of that evolution. It demonstrates that even in a world of advanced detection systems, there is still space for platforms that rely on a different set of strengths. And as long as warfare remains a contest of systems rather than individual technologies, that approach will continue to matter. If you want to understand where air combat is heading, you need to look beyond simple ideas like stealth versus non-stealth. Focus on the interaction between detection, tracking, and survivability, because that is where the real story is unfolding, and it is far from over. Subscribe to follow the evolution of modern military aviation, advanced fighter jets, radar systems, and the technologies shaping the future of air combat. How the F-18 gets detected. The real engineering breakdown. What if I told you that the F-18, one of the most iconic fighter jets ever built, is actually very easy to detect? Not because it's old, not because it's weak, but because it was never designed to hide. The F-18 is fast, agile, it can land on a carrier in a storm. But in a world full of advanced radars, how does it survive if everyone can see it? That's exactly what we're breaking down today. Real physics, real engineering, no hype, no politics, just the truth. If you want more breakdowns like this, hit subscribe. We don't do clickbait, we do how things actually work. Now let's start with the most basic question. What does detected even mean? Most people imagine a red alert, a missile locking, a pilot sweating. But here's the reality. Detection is incredibly simple. A radar sends out a signal. That signal hits something. A tiny part bounces back. That's it. The real question is not, can the F-18 be detected? The real question is, from how far and how clearly? Let me give you the answer immediately. The F-18 was designed in a completely different era, the 1970s and 80s. Back then, the priorities were speed, maneuverability, and carrier operations. Stealth? Not even on the list. Why? Because stealth comes with brutal trade-offs. Weird shapes that are hard to build, expensive paint that falls off, and you have to hide weapons inside, which means you can't carry much. The F-18 chose flexibility instead. Look at its design. External weapons hanging everywhere, big visible engine inlets, sharp angles and gaps. All of this reflects radar energy like a mirror. So yes, the F-18 lights up on radar. But here's the part nobody talks about. Being detected does not mean being vulnerable. Modern air combat is not about invisibility. It's about awareness, positioning, and timing. Let me break down how the F-18 actually survives. First, speed and maneuverability. The F-18 can change direction in an instant. It can pop up to high altitude or drop to the deck. Detection is not interception. A radar might see the F-18 from 50 miles away, but by the time an enemy missile is launched, the F-18 has already moved. Chaff deployed, course changed, the missile is now chasing empty sky. Second, electronic warfare.
This is where it gets really interesting. The F-18 has a radar warning receiver that listens for enemy emissions. It can tell the pilot exactly what type of radar is looking at him. Search radar, tracking radar, missile guidance radar. Different sounds, different responses. And then the F-18 can fight back. It can jam the enemy radar, send back garbage signals, make the tracking computer go crazy. Even if the radar sees something, it might not understand what it's seeing. Third, network warfare. The F-18 is never alone. It flies with AWACS, with other fighters, with ships and ground radars, all sharing data in real time. So while one enemy radar detects the F-18 already knows exactly where that radar is. Before the enemy even gets a solid lock, the pilot has already decided to turn away, or jam, or call in a strike on that radar. This is the part that changes everything. Now let me destroy the biggest myth in air combat. Myth: if radar sees you, you're dead. Here's the truth. Detection has layers. Layer 1, a tiny signal return. The radar operator sees a blip. No idea what it is. Could be a bird, could be a cloud, could be an F-18. Layer 2, tracking. The radar has to see the same blip multiple times to calculate speed and direction. That takes seconds. Layer 3, identification. Is it friendly, enemy, civilian? This requires more time and often a human decision. Layer 4, engagement. Only after all that does someone launch a weapon. Each layer is harder and slower than the previous one. The F-18 doesn't need to be invisible. It just needs to delay, disrupt, or outmaneuver each layer. By the time the enemy identifies the target, the F-18 is already gone. Let me give you a concrete engineering number. The F-18 has a radar cross-section, RCS, of roughly 1 to 10 square meters, depending on how many weapons are hanging off it. A stealth aircraft like the F-35 has an RCS of about 0.001 square meters. Do you know what that means? It means the F-18 can appear up to 10,000 times larger on radar than an F-35. Let that sink in. 10,000 times. That sounds terrible, right? But here's the twist. Modern radars are not just about range. They're about frequency, processing power, and networking. A low-frequency radar can detect stealth aircraft at much longer ranges because long wavelengths ignore most stealth coatings. And if you have multiple radars working together, they can triangulate any aircraft regardless of its stealth. So the F-18 is not as hopeless as it seems. In a dense electronic warfare environment, with jamming, decoys, and chaff, even a large RCS can be managed. Now let's talk about another type of detection that nobody thinks about. Heat. Infrared. The F-18 has two powerful engines. They get extremely hot. Infrared sensors can see that heat from dozens of kilometers away. The F-35 also produces heat, but its engines are buried inside the airframe and the exhaust is mixed with cold air to reduce the infrared signature. So again, the F-35 has an advantage. But advantage is not invincibility. Infrared sensors can be fooled. Flares are cheap and effective. Flying low in humid air absorbs infrared energy. And if you put the sun behind you, the sensor sees nothing but glare. The F-18 pilot has many tools to survive. Let me take you inside the cockpit for a moment. What does the pilot actually experience when the aircraft is detected? The radar warning receiver starts beeping. A display shows the direction of the threat. A computer identifies the radar type. The pilot hears a specific tone for search mode and a much more urgent tone for lock mode. Then the pilot reacts. Chaff, flares, jammer on, brake turn, dive low, climb high, call for support, all in a few seconds. This is why detection is not death. There is a whole chain of events between being seen and being hit, and the F-18 is designed to break that chain at every link. Now I want to ask you something. Is stealth overrated, or is it still the future? The honest answer is both.
For a country like the United States that can afford both stealth and non-stealth aircraft, the answer is to have both. The F-35 does the high-end missions, the ones where you need to penetrate dense air defenses. The F-18 does everything else: carrier patrols, ground attack, escort duty, air superiority when stealth is not needed. This mix is what makes the US Navy so powerful. They are not putting all their eggs in one basket. And here's something else. The F-18 is not standing still. The Super Hornet Block 3 is a very advanced aircraft. Better radar, better networking, longer range, more fuel, more weapons. It is still being produced today. Boeing has delivered hundreds of Super Hornets to the US Navy and to allies like Australia and Kuwait. The F-18 will be flying for decades. And yes, it will keep getting detected, but it will also keep surviving. Let me summarize everything in 5 points. 1. The F-18 is easy to detect because it was not designed for stealth. 2. Detection is not the same as vulnerability. There are many steps between being seen and being hit. 3. The F-18 survives through speed, electronic warfare, networking, and pilot skill. 4. Stealth is just one tool. It has serious trade-offs. 5. The F-18 is a versatile workhorse that will remain relevant for a very long time. So next time you hear someone say, "This jet isn't stealthy," remember this breakdown. Detection is just the beginning. The real battle starts after the radar sees the target. The F-18 is not trying to be invisible, it's trying to be effective, and it succeeds at that every single day. Now I want to hear from you. Do you think stealth is overrated, or is it still the future of air combat? Write your thoughts in the comments. And if you want real engineering explanations without the hype, subscribe. Thank you for watching. I'll see you in the next breakdown.